Okay, so this is lesson 6. This is the last lesson of unit 4. In fact, the last calculus lesson, all right? And I would say, other than finding maxes and mins using derivatives, in terms of what we do in this course, this is probably the most important application, because this is an application that you see everywhere. So this is, well, you know what, let's take a second before I actually give you the title here, okay? Because we'll kind of get to what we're doing in our first example. So what I'm going to be doing here is I'm going to go through the first 4 questions. There were already videos made for questions 5 and 6, so I'll leave that for you to work on. Again, would be even today, what I'm going to do is I'm going to pause the recording to have you try at least drawing the diagram, maybe coming up with an equation on your own. All right, so let's get started. And again, please just chime in either by chat or by your microphone when you have a question, okay? So I want you to look at this question, and I hope you're going to see that it looks kind of familiar, because we've seen a question like this before. So it says an oil spill from a tanker spotted, blah, blah, blah. Helicopter surveillance measures the radius of the spill to be increasing at a rate of 0.5 meters per second, okay? Now, does anybody remember what we use this type of example for? What were we trying to get to in this particular example when we saw it in advanced functions? Any takers? Yeah, exactly. When we were talking about composite functions, because here we saw that, well, wait a minute, you know, it says the radius is increasing at a rate of 0.5 meters per second. So it seems to be telling us that the radius is a linear function of time. But then, of course, when I look at this first example, you know, the circumference I know is is a function with respect to radius. So we were able to write, you know, circumference, which is normally a function of radius, but then radius itself is a function of time. So we realized that this could be seen as a composite function, and we can find a function for circumference directly with respect to time. Okay, now this is a bit of a special example because, you know, we're assuming that the rate of increase is constant at 0.5 meters per second. So if we assume that, then we can certainly come up with an equation. Okay, but that won't always be the case. But I want to use this simpler example to get to something new. Okay, so let's consider how circumference is related to time. Okay, we all know this, so I'm not going to bother asking. So we know that the circumference is given by 2 times pi times r. But here we're not interested in calculating circumferences, okay, like we were when we were doing this example for composite functions. We're actually looking for, it says, how fast is the circumference increasing with respect to time? So what is it that I'm looking for? And maybe we can use the more common name for what I'm looking for and the more mathematical name, okay? So there you go. What we're looking for is the rate of change of circumference with respect to time. And of course, we know that in this course, when we talk about rate of change, we're talking about the derivative, okay? So first things first, we're looking for the rate of change of circumference with respect to time, not with respect to radius, okay? But we know what the rate of change of the radius is with respect to time. So instead of writing this composite function, which again, we could only do because of this very special scenario that r happened to be a linear function, is let's just use what we saw yesterday when we were talking about implicit differentiation, is let's just take the derivative of both sides of this equation and see what happens. Okay, so somebody I think was asking a question, but I didn't quite get that. Or was it just a little error? Okay, so I'll assume just a little error there. Okay, so let's take the derivative, again, with respect to time. So for now, eventually you're going to see me using prime notation, but I really want to be clear at this point that I'm taking the derivative with respect to time. Okay, so there's really nothing to do here because I don't know what c is with respect to time, okay? But I can do a bit with this derivative. And if I want to take the derivative of this function here, well, 2 pi is just a constant. So it's just going to be equal to 2 pi times, well, the derivative of radius with respect to time, okay? And I want you to look at this equation, okay? Because what I now have is I have an equation that relates the derivative of circumference with respect to time to the derivative of radius with respect to time, okay? So our original function related the circumference with the radius. This now relates to different objects. It represents the derivative of c with respect to time and the derivative of r with respect to time. So it relates these two rates. And so this is why we call this a related rates equation. Okay, because it's not just relating two variables, it's relating the derivatives of two variables, okay? And hence this is called a related rates problem. How can you use the knowledge of one rate to determine another rate? So how can you use the knowledge of one derivative to help you determine the other derivative, okay? And hence the title for this lesson is these types of questions are called related rates problems. Okay, and we'll talk a little bit as we go along how this, comes up, as I add, a drop of my reactant, at 1 milliliters per second to my so if that's the, and I'm trying to pretend I know chemistry here, but if I add, a drop, a millimeter per second of a reactant to a solution, how is that going to affect the rate of the chemical reaction? Okay, so that's one example. This is another example where we relate the rate of the radius changing to the rate of the circumference changing. And so now, can we solve this problem? Well, I'm looking for dc dt, so now I'm going to allow myself to use this prime notation. But remember, we have to keep in mind that this prime notation represents not the derivative with respect to r, but the derivative with respect to time. Equals 2 pi times, and what is dr dt equal to? Okay, let's go, folks. Let's try to chime in a little quicker. There you go. That's what they told us. They told us that the radius was increasing at a rate of 0.5. So this is why not only is it going to be 0.5, it's going to be positive 0.5, because if they were telling me that it was decreasing at a rate of 0.5 meters per second, I'd have to use a negative number. And there you go. So what is the rate of change here? Well, this 2 times 1/2 is just 1, so it's just going to be pi, and in this case here, meters per second. Okay? So now what I'd like you to do is I'd like you to try this exact same scenario, okay, given this information, to do part B, okay? So I'm going to give you about a minute. I'm actually just going to stop the, yeah, so here, I don't know if you can see this. Jacob is saying if the radius is equal to 0.5t, couldn't you just plug in that formula? Yeah, so that's what I talked about earlier, is that this is a very easy problem because I could have actually just come up with a function of c with respect to time. For sure, I could have done that. I'm just using this example to kind of lead us to a different way to approach this, because your inside function isn't necessarily always going to be a linear function that you can write quite so easily, okay? So 100% you could have done that, okay? I'm just offering an alternative way of solving this problem, which is then going to lead to, kind of like we did with the circle yesterday, is we could have done it via traditional methods, but hey, it turned out using implicit differentiation turned out to be useful. Okay, so I'm going to stop. I'm going to give you about 2 minutes to try to come up with a solution for that second one. There we go. We're back. Sorry, I forgot I had muted myself. All right. So if I do the same thing here, because I have a formula for A with respect to R. So A is equal to pi r squared. So again, I'm going to take the derivative with respect to t of both sides. All right. So this is just going to be, so again, I'm going to use this prime notation, but I'm going to keep in mind that this represents the derivative with respect to t, equals to, well, here pi is just a constant. Now this is where I have to be careful, because now I'm not taking the derivative of r squared with respect to r, I'm taking the derivative of r squared with respect to t. So who's going to remind us what we need to use here in order to take this derivative correctly? All right, there you go, good old chain rule. So as before, first I'm going to take the derivative of the outside function, so that's going to be 2r, and then I'm going to multiply it by the derivative of the inside function, which is just dr dt, or r prime. Okay, and remembering that prime here represents the derivative with respect to time. So now what we have is we have a related rates equation. So a prime is equal to 2 pi r times r prime. Okay, and so we just go back and we say, yes, r prime is equal to 0.5 meters per second. So I can just replace r prime by 0.5, and that'll help me determine a prime. And I hope everybody saw that there's a problem. So what is the problem here? Why am I not able to solve this problem? Okay, so anybody else? There you go. As we realize that in this circumstance, I do have a relationship. It is a related rates equation because a prime, it can be written in terms of r prime, but we still have an r left over. Okay, now I don't think this should be too surprising. Okay, so a bit of a freeze there, so hopefully it'll come back soon. There you go. And what was special about this particular relationship that kind of led to the fact that I was able to solve this problem so easily? What is special here? There you go. This happens to be a linear relationship, so it shouldn't matter at what moment in time uh, you're considering, whereas this is not a linear relationship. Okay, and so this is, more often than not, we will not be working with linear relationships. All right, so you can't solve this problem as is. What I could have said is I could have said, how fast is the area changing with respect to time, if r is equal to 3. Okay, I guess here 3 meters. Okay, this is certainly a question I have. So very often you're going to see that when you're working with a related rates problem, it's not as simple as you give me one rate and then I can find the other rate. You're often going to need some extra information. Okay, so now if I change the problem here, well, I can solve it because it's just 2 pi times 3 times 0.5, and what is that? That's just 3 pi meters squared per second. All right, because here now we're talking about area, and it makes sense because in math we don't write the units, but in physics this is why they force you to write the units all the time, because this is meters per second, and then you're multiplying by meters, so it gives you meters squared per second. All right, so this is the general idea for a related rates problem. Okay, the idea is that you have some relationship between two variables, and by taking the derivative of both sides, you can find a relationship between their rates or their derivatives. All right, and then from there, with the information given, you can solve the problem. And very often you need something more than just the rate. You're going to need some other information. Okay, now the bad news is that you're not always going to have something which is quite so straightforward, because here, hey, the circumference of a circle, the area of a circle, these are established relationships that we already know. We didn't have to do any work to come up with the area or circumference. Okay, in most of the other problems, step number one is to come up with the model first, and then from there take the derivative with respect to both sides. Now, the other thing that you're going to notice, and I want you to take a stab at it now, is these rates that we're talking about. Okay, and even if you think about the example I gave about, adding the, using your dropper to add a reactant to a solution, what do you think these rates are with respect to? Any ideas? Usually when we think about how quickly something is changing, exactly. So Jamie, there we go, Anna, with respect to time. So almost, in fact, I think every question in this grouping here is going to have rates with respect to time. That a related rates problem is almost something that's with respect to time. So this really is focused in on applications, okay? And you'll kind of see, we'll make references to how some of these problems are related to more real life problems, all right? So let's just take a quick look at the second one, and I'm going to give you a bit of time to, not surprisingly, draw a picture and hopefully come up with a related rates equation, okay? So you have a UFO that flies horizontally directly above UFA, okay? They give you the speed and they tell you how high it's flying in the air. And they want to find the rate of change at which the distance from the UFO to UFA is changing, okay? And notice here how they're giving you this little extra piece of information, okay? So the fact that they're saying that they want the rate of change when it's 20 kilometers away is giving you a hint that at some point you're going to need this piece of information. All right, so I'm going to stop the recording for, again, a couple of minutes. What I want you to try to do is draw a diagram that relates to the situation. All right, and then see if you can come up with a related rates equation. If you have time to start solving it, that's great. All right, so go ahead, give you a couple of minutes. Okay, so we're back, okay. So here, does the 20 kilometers. So here, what we're gonna assume is that if they're just saying the distance between the two objects, then you should be just drawing the straight line that joins them, okay? You're gonna see in another question, they're a little more specific as whether they mean a vertical distance, a horizontal distance. So in this case here, it would be the diagonal because it's just whatever the straight line is between them. Okay, so how do I approach this problem? So I try to, first of all, is just to figure out what's going on. So, I've got this place called UFA. So let me just draw it. Now again, we kind of know that UFA is a school. So, we know that it's, it lives on the ground. Okay. And then you have this UFO that's flying directly above, okay, and it's flying horizontally, so they're being pretty specific here. We don't even really have to make too many assumptions here, okay, and it's traveling at an altitude of 10 kilometers above, okay. So there you go, there's my UFO, and the distance, okay, is 10 kilometers above UFA, okay. And let's see what they want to know. They want to say, find the rate at which the distance from the UFO to UFA is increasing when it's 20 kilometers away, okay? So what we're interested in is the rate of change of the distance between the school and the plane. So I'm going to represent that as I just talked about here. I'm just going to represent that with the straight line joining them, okay? And as I've done in the past, I'm going to use capital D here because I know I might bring in some derivatives and I don't want to confuse things. So I'll use capital D. And okay, so I want to find the rate at which this is changing. So if this is a related rates problem, what other rate have I already been given? So what's the other rate here? Yeah, they're giving me the speed of the plane. So they're telling me how fast this point or this UFO is moving along in this direction. And is there something that maybe you see in this diagram that would be of use? Something that seems to, there you go, good old Pythagoras. So the idea here is to create a right angle triangle and set it up hopefully as a Pythagoras problem. Okay, so I already know this side is 10. This side length here is the rate. Clearly if this is moving away, this distance is getting larger, okay? And so what I need is I need some representation of this distance that's traveled. So I saw somebody suggesting X. So if I use X to represent this distance here, I can now create a relationship between the two distance variables. Okay, so here we can write x squared plus 10 squared is equal to d squared. Okay, so as we had, okay, so I'm gonna deal, so Astrid's asking a very good question. I'm gonna deal with that in a second. Okay, so here we go. Here's our equation that relates our two variables. The goal now is to find the equation that relates the two rates. Okay, now this is a very good question. Should we input the 20 onto the diagram? And you may have noticed that I did not input the 20 on the diagram. Now, by the way, why did I allow myself to input the 10? Why do you think I didn't worry about inputting this 10 here? Can somebody tell me why I had no? There you go, because 10 is a constant, okay? It's traveling horizontally, so this vertical distance is always going to be 10. So that's why I allowed. But this is what I want to remind you of, is that when you're finding the derivative at an x value, you put the x value into the function and then take the derivative? No. What you do is you always find the derivative first and then you input the x value. This is a particular moment in time, okay? Because this UFO is going to be at many distances away from UFA. Okay, I want to determine the rate of change at this particular moment in time. And so it's very important that when they give you this specific information, which changes over time, that you only inputted it after you take the derivative. Okay, so let me know if does anybody need me to explain that again, because that is one of the most important sort of points in solving these questions. Okay. Okay, so I don't input the 20 into the diagram because this represents a distance at one particular moment in time. So I'm only going to be inputting that after I've taken the derivative. Okay, now I'm interested in dt because I want to know this rate of change. So I could certainly solve for d and rewrite this as d equals the square root of x squared plus 100. Who's going to tell me why I'm not going to do that and what my alternative is? There you go. So somebody is suggesting is to just deal with this as an implicit relationship and use implicit differentiation. And what that does, these are very simple things to differentiate implicitly. I don't have to deal with square roots. I don't have to deal with anything to the negative 1/2. So now we're starting to see how this implicit differentiation, even in a much simpler scenario, works pretty nicely. Okay, so what I'm going to do now is I'm going to differentiate both sides, but differentiate with respect to what? This is what's important, is what type of derivative am I interested in? Okay, so I see a couple of x's, a couple of t's. Well, when we talk about the rate at which the distance is increasing, okay, it could be with respect to this variable x, but it also could be with respect to time. But when I look at the information that's given, it's a rate with respect to time, okay? So again, so Jacob, you really like that writing as 600. You certainly could write it that way, but I actually think it's going to be nicer not to do that, okay? I think it's nicer to go ahead and use just the related rates instead of coming up with an equation for this distance here, okay? So what I'm going to do here is I'm going to take the derivative of both sides with respect to t. Okay, so the derivative of x squared, this is where, again, I got to remember I'm taking the derivative with respect to t, so I have to use a chain rule. So it's going to be 2x times the derivative of x with respect to t, which again, I'll allow myself to use the prime notation because it's getting annoying to write d dt all the time. Derivative of 100, regardless of what the variable is, this is still a constant, always equal to 0. And then here, something very similar, 2d times dd dt. Okay? Now, I just realized I should have written d prime. I guess I wasn't thinking there. Okay, should have written d prime there. But it doesn't matter. means the same thing. Okay, now this is the thing I'm looking for. What do I know? So, sorry. That based on time. Sorry, could you go over why the derivative? Because that's the type of rate of change that I'm interested in. Okay, when I'm interested in how a distance is changing, I'm usually interested in how it's changing with respect to time. Okay, and in this case here, the other rate that I'm given is also with respect to time. So as I said, sort of as part of the question one, is we're almost always interested in rates with respect to time. Okay, is that okay? Okay, so this is what I'm looking for. This I know is 600 kilometers per hour. Okay, I know the value of d at my specific moment in time. Okay, that's 20, so I know this is 600. Okay, this is 20 because that's the particular instant in time I'm interested in. This is what I'm looking for, but I still have this x value. So that seems to be a problem until somebody's going to tell me why it's not actually a problem. How can I deal with the fact that I still have this variable that wasn't given to me explicitly? There you go. Is that now I'm looking for this x value at a particular moment in time. So I can calculate what that is because now I'm given that my d is equal to 20. I know that this is equal to 10, and I'm just looking for that particular x value. Okay, so here I just have x is equal to the square root of, well, 20 squared minus 10 squared. So what is that equal to? That looks like the square root of 400 minus 100, 300. Okay, so now I can input everything into my equation, and the only thing I have left is going to be dt. Okay, so I have 2 times square root of 300 times 600 equals 2 times 20 times d prime is that thing that I'm looking for. Okay. Okay, so somebody asked about why I have this, because remember, this is, I'm taking the derivative with respect to time, so I have to use the chain rule, okay? So that's why I first took the derivative of this outside function, so derivative of x squared is 2x, but then I have to multiply by the derivative of the inside function with respect to time, okay? So it's just me using the chain rule, okay? And there you go, now I can just solve for d prime. So d prime is just equal to, so what do we have? We have 2 times root 300 times 600 over 2 times 20. 2's cancel out, 10's cancel out. This just becomes 30. So that looks like 30 times root 300. And since this is an application question, I certainly expect to see an approximated answer. By the way, folks, remember you're always checking my algebra here. Make sure my algebra is okay. So 30 times 300 exponent 0.5, and that's 519.6. So that's about 519.6 kilometers per hour. Okay. And again, this idea that when we're talking about a speed, we want to talk about how it's changing with respect to time. Okay. It's not that we're never interested in the rate of change with respect to another variable, but often it's time. Okay, so Ali, do you want to maybe ask it out loud, if you don't mind?
Yeah, so I have a question.
Yeah.
For the derivative, the first derivative of x, it's 600 kilometers per hour. Shouldn't we change it to Oh, never mind. Never mind.
Everything's in kilometers.
Yeah, never mind.
Yeah, but I'm glad you brought that up, because don't ever just assume, that you need to take a look. And we saw there was one example where we had, I think it was the jewelry box question, where we did have to keep in mind that the the units weren't all given in the same way, okay? So while it's not necessary in this case, it's one of those things that you should always have in the back of your mind, okay? So now, what we've seen so far, and again, not completely unrelated to what we've seen in our optimization portion of the unit, is we're seeing that we need to use our measurement formulas. Here we see that we're using Pythagoras, okay? Maybe there's some other interesting things that you've learned in the past that are going to come up in the next set of questions, all right? So any last minute questions before I move off for this one? Okay, so let's, so the plane was, yeah, the plane was traveling at a constant speed, okay? But what I'm doing is I'm just circumventing having to write a function for this here, okay? You're able to work completely by just relating the rate of change of this distance to the rate of change of that distance, okay? Okay, so again, we could have probably solved this in a different way in this particular scenario, but this, in the end, is probably a little faster. And again, it won't always be the case that everything is a linear relationship, okay? So let's take a quick look at number 3 before I give you some time to work on it. And again, it's another one of those questions, fairly straightforward, I'd say this one here, but without a good diagram, it might be tough to see it, okay? So one thing I'll let you read it and give it a try. One thing I want you to keep in mind is that now some of the information that you're given or you're being asked for now has to do with angles. Let's take a look. Oh, sorry, let me go back. I see Jacob's asking, could it be solved without the 20 kilometers? No, okay? Because in the end, look at everything that we had once we took the derivative, okay? You needed that 20 for this unknown, and then you needed the 20 to solve for that unknown, okay? And even if you did it with respect to time, you would need to know either that 20 and you'd have to determine a time value, or you'd have to be given a time value, okay? So take a look at this next one. And again, the goal is to get a good diagram. I think you're going to be using something a little different in this question here. So I'll give you maybe 3 minutes to work on this one. All right, we'll start up again in 3 minutes. Okay, so we're back here. So let's take a look at what's going on. We have a balloon that's rising straight up. It's tracked by a rangefinder 500 meters from the liftoff point. Okay, so let's draw the ground here. So draw it a little lower since it's going upwards. So if I call that, the liftoff point, I've got my rangefinder here, and it's 500 meters away. Now again, why am I allowing myself to write a particular number? We talked about being wary, okay? So yeah, very good. It's a constant, it's not gonna change. This rangefinder stays where it is. The liftoff point is the liftoff point, all right? So it says, at the moment that the angle of elevation of the balloon from the rangefinder is pi/4, the angle is increasing at 0.14 radians per minute. How fast is the balloon rising at that moment? Okay. And if you're wondering why I'm writing this, it's because years ago I had a student who would call me out on anything that wasn't very explicit. And so I started to learn to be a little more explicit about everything. All right. So let's see what we have. I have this balloon that's moving up. Okay. Upwards, okay, and I want to determine how fast the balloon is rising at this point here. So if I call this the height of the balloon at any one moment, I want to know how quickly that's rising, again, with respect to what? With respect to time, all right? But the information that I'm given, okay, has to do with the angle of elevation, all right? So The angle of elevation, we know, is given by the the horizontal, and then since it's elevation, we're moving upwards, okay? So I'm gonna have to draw this line here to join the rangefinder to wherever the balloon is, all right? And I'm interested in the angle of elevation, which I'll call theta, okay? Yet again, I'm not even gonna bother asking because hopefully it's you know, fairly straightforward. Again, rising straight up. I probably needed that for my old student. So because it's going straight up, it means I've got a right angle triangle. Now I had a right angle triangle in the last problem, except I'm not going to be using Pythagoras here because I realize that I have no information about the third side of the triangle, and I'm not interested in the third side of the triangle. But what I do have information is or I have information about this angle, okay? I know how quickly it's changing, how quickly it's increasing, okay? H and the horizontal are at, wait, H and the horizontal are at the same right? Sorry, Enoch, I don't understand the question. Oh, no, stop, folks, stop. That was by, no, whoa. Remember, what do I not have on this diagram? What do you notice I do not have on this diagram? I do not have the pi over 4, okay? Because the pi over 4, is this angle of elevation always pi over 4? No, okay? It changes over time, okay? This represents one particular moment in time, which is why I'm not putting it on my diagram because I don't want to incorporate this. So when it's exactly equal to pi over 4, will this side and that side be equal? Okay, yes, okay. But what I'm trying to represent here is a general moment in time, okay? And this is one of the most important things to remember when you're drawing these diagrams. So when I look back at number 2, okay, you notice I didn't put the 20 on my diagram because that's representing a particular moment in time. What my diagram has to represent is a general scenario, okay? That's going to be very important when you're drawing some of these other diagrams, okay? So let's make sure that at this point, my diagram, these do not have to be the same, okay? Will they be the same at exactly pi over 4? Sure, but I want to draw something that's more general. Okay, I can't use Pythagoras because of that third side. What am I going to use though? What other relationship do I have with a right angle triangle? I have trig ratios and more specifically, the tangent ratio, okay? So that's going to be the relationship that's going to relate these two variables because I can just write that tangent of my angle theta is just equal to the opposite over the adjacent is equal to h over 500, all right? So this is the relationship I need between the two variables, all right? Now, now this is something I do want to talk about. That notice that what this says here. It says that at the moment when the angle of elevation of the balloon from the rangefinder is pi over 4, the angle is increasing at 0.14 radians per minute. Can we assume here that this rate is a constant rate? And in fact, why does it not make sense that it would be a constant rate? Why does that make perfect sense? Because it says, now I want you to tell me physically, what do you think we can't assume about how this balloon is moving? There you go. I cannot assume that this is moving at a constant rate upwards, okay? So here we have an example where this rate of change that's given is at a particular moment in time. So we can't do what would have been an option in the other two questions, okay? So there we go. We're going to have to use implicit differentiation. So what am I going to do? I'm just going to take the derivative with respect to time of both sides. Okay, so here I'm taking the derivative of tan theta with respect to time. Well, I'm going to have to use the chain rule. Okay, so this is, this is my u. So first I'm going to take the derivative of the outside function. And we know that the derivative of tangent is secant squared. So we have secant squared theta, but then we have to multiply it by the derivative of theta with respect to time. Okay, derivative of the inside function. All right, and here, well, 1 over 500 is just a constant, okay, times, well, hey, just the derivative of h with respect to time, okay? And what do we have? This is our related rates equation, okay? So it's the equation that relates the rate of change of the angle with the rate of change of the height. And we are now seeing why it was important for them to give us a particular angle, okay? Because we have this secant squared theta that's hanging around. Okay, without this information, we wouldn't have been able to solve the problem. Okay, so now we just input what we know. Where's that quotient rule? So somebody talks quotient rule. So definitely not quotient rule here because that's a constant. It's much, much easier to just take this 1 over 500, which is a constant, and then multiply by the derivative of h. If you use the quotient rule, yeah, you could, but boy, that would just be, much more work than necessary, and even worse, much more possibility of making a silly sign error. Okay, great. So let's put in what we know. So we have secant squared of pi over 4. Okay, d theta dt at that moment in time we know. So now we've taken the derivative, we can start inputting the individual things. So 0.14, okay, and then equal to 1 over 500 times that thing we're looking for, and that's the only variable we have left. Okay, now for sure this is secant of pi over 4. I can find the exact answer, but since I'm going to be looking for an approximation anyways, I might as well just throw the whole thing into my calculator. Okay, so just check my calculations as I go along. So here I've got, so secant is just 1 divided by cosine of pi divided by 4, and I just take a quick check. I am in radians. Okay, so equal to, and then we're squaring that. Okay, we're multiplying it by 0.14, and then I'm just going to multiply 500 to the other side of the equation, so times 500. Okay, and it looks like we have 140. Okay, so dh dt is equal to 140, and what are my units here? Well, distance was measured in meters and time was measured in minutes, so this is meters per minute. So that's how quickly the okay, yeah. So so what I see here, so and DHT is what question is asking us to find. Exactly, because they're asking here, how fast is the balloon rising at that moment? We realize that that represents the derivative of height with respect to time. Okay, so before we move on, I just want to think about how you might, I don't know how important it is to know how quickly a balloon is rising with respect to time. It might be, I suppose, if you're studying some sort of meteorological phenomenon, maybe this would be important. But one thing I was thinking about here is this might be something that a speed detector might be using as technology. Okay, so you sort of have to think you've got a detector that's further up that's detecting, the motion of a car moving, and maybe it can measure how quickly the angle of the probe is moving with respect to time, and then it can use that and the height that it is above the ground to measure how fast the car is moving. Okay, so again, finding a way to relate something that the actual machine can calculate, so the rate of change of angle with respect to time to help you calculate another rate of change, the speed of the car. Okay, so these are the types of applications where this whole related rate thing comes into play. In fact, you'll see another one, I think it's number 5 or 6, I don't remember which one, has a similar type of scenario. Okay, so now we've added another thing. So we've seen our measurement formulas, we've seen Pythagoras, and now we've seen our primary trig ratios. Okay, the last one we're going to do, how did we go from radians per minute to meters per minute? So before I go on, so this again, this is I guess where you know, the physics thing, maybe now I'm starting to see why it's good. So let's take a look at what we have here. So this represents radians per minute, okay? This here, the 500, when you multiply it to the other side, you get a meters in the numerator. And this is where you have to remember that radians doesn't actually have a unit, okay? Remember that, you know, we kind of call it radians, but it's a unitless measure. And so what you're just left with is meters per second. Okay, which makes sense because what this rate of change represents is a rate of change of a height, which would be measured in a distance unit, meters, okay, per, and our unit time in this case here was minutes. Okay, so hopefully that that solved that one. Okay, so if we take a quick look, before I go, I actually better make sure, any other questions on that? All right, so let's move on to the last one that we're going to do right now. Now, again, number 4, when you draw it, you know, you're going to see again maybe some similar looking shapes as we've seen before in this lesson, but I think you're going to actually have to use something different, something that we haven't seen before, but something that's also very common in a lot of these problems. Okay. And by the way, this question is an homage to Randy. So if you've done any of Randy's interesting Wednesday sessions, this is an homage to good old Randy. Okay, so I'll give you a couple of minutes to try to set it up and see if you could come up with an equation and see what other maybe geometric property might be useful here. Okay. Okay, folks, so we're back here. So we've got a 2.4 meter Sasquatch walks away from a 5 meter lamppost at a rate of 1.6 meters per second. And what rate is the length of the shadow growing when it is 10 meters? Okay, so here notice that it's specifically saying horizontally from the lamppost. All right, so let's, again, I think drawing a diagram here is going to be helpful. So we've got our lamppost. Okay, and we've got, I guess, our Sasquatch. I'm not very good at drawing Sasquatches. Get big feet there, and I guess maybe some arms. There we go. Give him some long, crazy hair. There we go. There's our Sasquatch, or at least as good a replica as I can give. I haven't seen one myself. You can ask Randy what they look like. All right. So what else should I be drawing here? Because I'm interested in its shadow. There you go. I'm going to draw, because I think I got this light that's going all over the place, but what's going to start causing the shadow is the light that's being blocked by the Sasquatch. Okay, so that's the light that stops being blocked. And so if I draw this triangle, okay, and I know that this is the length of the shadow, okay, so let's call this, you know, I don't know, S for shadow, okay, and what is the rate that I'm given? Okay, because I want to see how this length is. Okay, the speed is walking, okay, but I notice here that my diagram is a whole bunch of distances. So how am I going to add a distance? There you go, this other part of the segment, because what I'm looking at is we know he's walking at, what is it, 1.6 meters per second away from the lamppost. So it's essentially the rate of change of this distance here, okay? So if I call this distance, say x, I know what this rate of change is. It's going to be positive 1.6 meters per second because he's walking away from it, so this distance increases, okay? And I want to know how this shadow changes with respect to time, okay? And I see a very interesting suggestion. So before I take a look at this suggestion, let's take a look at some of these numbers here. Can I put the 2.4 meters into my diagram? Yeah, because the Sasquatch, we're going to assume, doesn't change height, okay, throughout this process. So I have this as 2.4 meters. Can I put the 5 meters into my diagram? Yes, again, yeah, very good, because this pole is, you know, not changing height, okay. Am I going to put this 10 meters into my diagram? No, because this, you know, is at a particular moment in time. When it is 10 meters from the lamppost, it's only 10 meters away from the lamppost at one particular instant in time. Okay, so I'm not going to add it in. That's only going to come in once I've taken my derivative. Okay, so again, hey, I see triangles. Not only see triangles, I see lots of triangles. Okay, now let's do a quick check, because normally when I see a triangle, I guess my first thought is Pythagoras, okay? And hey, look, I'm interested in this side of the triangle. I know that side length of the triangle. The problem is I neither know this side of the triangle, nor am I interested in this side of the triangle, okay? Similarly with this larger triangle, okay? Oh, x represents the distance of the Sasquatch to the lamppost. And since he's moving away from the lamppost, this here represents the derivative of x with respect to time. Okay, it's how this distance from the lamppost changes with respect to time. Okay, so Pythagoras is out the window. Oh, wait a minute, we just used primary trig ratios, but I don't have any information about this angle or that angle, and I'm not really interested in the angle, okay? And I lost it now because a whole bunch of yeses and nos came up, but somebody brought up something else. Because another thing we have at our disposal is, hey, not only do I have two triangles, what is, I guess I'm trying not to use the word, what is common with respect to these two triangles? That's it, they're similar triangles. And we know that similar triangles have ratios, side length ratios that are equal, okay? So if I take two sides that are corresponding to each other, the ratio of these two sides is equal to the ratio of any other two sides, okay? So let's start with the smaller triangle, okay? I'll put the variable on top, always try to do that if I can. So I can have the ratio s over 2.4, okay? And I know that the ratio is going to be the same in the bigger triangle, okay? So what side length in the bigger triangle is corresponding to the 2.4? The 5. Good. Okay, this side here, because remember the idea of similar triangles is they have to share the same angles. So actually this is nicely set up because this angle here and the 90 degree, okay, shared within those two triangles, so the 5, okay? However, when I look at the S, what would be the corresponding side to S in the other triangle? There you go. So somebody suggested X plus S, and that's where you have to be careful. You know, sometimes people just say, oh, it's X, put it in there. Well, no, not quite. It's this whole side length. So X plus S is the corresponding, I just got to make sure this doesn't look like a 5. I'm starting to regret having chosen S here. Okay, and there we go. We've got our equation. Okay, now here we can, You know, I suppose we can multiply things out, but I don't think that's actually necessary because now I can just take the derivative of both sides if I like, and then solve from there. All right. So why isn't 2.4 in the same part of the fraction as the 5? So there's a couple of ways to write these relationships. You can write 2.4 is to 5 as s is to x plus s. You can write it that way, but you can also write it, you know, using two side lengths in one of the triangles, in the smaller one, and then relating it to the corresponding sides. It ends up being equivalent, okay? So it actually ends up being, whichever way you write it works just as well, okay? But look what I have now. I now have a relationship between s and x. Okay, what's the next step? There you go. I'm going to differentiate both sides with respect to, and again, what am I interested in? I'm interested in the derivative with respect to t. Okay, so we have d dt of s over 2.4 equals d dt of x plus s over 5. Okay. By the way, I think it might have actually been a little simpler had I used the other way, but in the end, this will work out, no problem. Okay. Am I using quotient rule here? No, I don't need to because 2.4 is just a constant. So this is just 1 over 2.4 times ds dt. Okay, equals, okay, again, the 1 over 5, that's just a constant. This is just a sum, so it's just going to be dx dt plus ds dt. Okay, and so now let's input, now that I've taken my derivatives, let's input what we know. And what do we know? Well, we know dx dt, which we have there, perfect. So we have, 1 over 2.4 ds dt, okay, equals 1 over 5 times dx dt was 1.6 meters per second, okay, plus 1 over 5 ds dt. Yeah, this definitely would have been nicer doing it the other way, okay? And then what's the last thing we have to do is let's bring together all the ds dt's, okay? So I'm going to have ds dt, bring that to the other side. So I'm going to factor it out. I'm going to skip the step and factor it out. What do I have? 1.1 over 2.4 minus 1 over 5. And then here I've got 1.5, 1 over 5 times 1.6. Okay. Notice here, I don't worry about putting everything together because I'm going to be looking for an approximation anyways. So I'm going to let my calculator do all this work. Okay, so ds dt, and again, I hope everybody's taking a look at my algebra because I might have overcomplicated this a little bit, okay? But it should work out, so no worries. Okay, so let's calculate that. So we have 1.6 divided by 5, okay, 0.32, and then I'm gonna divide that by, make sure you open up a bracket, so 1 divided by 2.4 minus 1 divided by 5, and we get, looks like it's about 1.5. Okay, so somebody asked a question about, yeah, there we go. I moved this whole thing to the other side, so it became minus 1/5 ds dt, and then I factored out the ds dt, and this is what was left over, okay? Okay, everybody got that? And again, this is where, I'm allowing myself, by the way, if I personally was writing a test, there's absolutely no way I would have done this in one step. I would have written out another step, okay? Okay. The only thing that would have been simpler is maybe if I had written 2.4 over 5, actually, you know what? Maybe it wouldn't have been simpler. I don't know. I feel like I haven't looked at the solutions of the ones I posted. I already posted solutions to this. I feel like it was a little simpler. I probably just set it up a little different. So you can take a look at that one, okay? And let's just make sure we have the right units. And what were our units? It was meters per second, okay? Okay. Now, I see that Ali was sort of a step ahead of me because he's asking the question that I was just going to ask you. You know, I tried to sidestep it because in inputting what I knew from the question, I was going to ask you, did you notice that there was something that never came into play? Okay. And you realize that, you know, you never actually used the 10 meters away from the lamppost. And hence, clearly, it must not matter. Okay. So you were able to, means that the shadow is changing at 1.5 meters per second. Now, by the way, you notice that the answer came out to be positive. That means that the shadow is also increasing over time. But imagine, you know, if you don't believe me, go outside tonight when there's no one near 6 feet away from you, and there's a lamppost, and you'll see that as you walk away from the lamppost, you'll see your shadow getting bigger and bigger and bigger. Had it been getting smaller, it would have come out in the algebra. But who wants to tell me why it's not so surprising that it shouldn't matter? Why should it not matter how far you are from the lamppost? Take a look at that original equation. There you go. You realize that if you rearrange this equation, this is actually a linear relationship between x and s. And so in the end, it makes perfect sense that it shouldn't matter how far you are from the lamppost, that the rate of change should be constant because the relationship between those two variables is linear. Okay? So again, this is one of these scenarios where, you know, I don't know that you'd be able to come up with this equation without drawing a diagram. So very, very important to be drawing the diagram. All right. So is there a way of solving this that uses the 10? I don't know. I don't know. I can't think of a scenario where it would ever come into play because it would be a bit of an issue if it came into play. The only way it would ever come into play is if the 10 showed up twice. So for example, yesterday I solved the problem with the cost, where the cost was twice as much in the tutorial. So in the end, it worked out that it canceled out, but it's not really coming to me as to how that would come about in this type of problem, okay? But certainly if the 10 ever came into play, it would have to be then canceled out at some point, okay? So if let's just take a quick look, you'll see that the notes don't have much to it because, you know, the actual procedure is always the same, but doesn't really help you solve the problem that much. Okay, oops. There we go. So essentially, what does it tell you? It says it refers to some relationship that involves two derivatives. Okay, it specifies here the derivative is, you know, almost always with respect to time that you're interested in. Okay. It reminds you that very often, not all the time, one of the functions or sometimes both of the functions might actually appear in your related rates problem, okay? Like it did in questions 2 and 3, all right? And very important, this is like a little warning that you only put in specific values of the variable after you've taken the derivative. Things that are always constant, like the height of the pole or the height of the plane, you can put in because they're constants. Whereas things like, you know, the distance away from the lamppost changes over time. Okay, so maybe one last thing I'll do is I'll just go over. So I'm being asked to go over how I set up this relationship here. I used similar triangles. So what I did is I have my big triangle here, which has side lengths. This whole side length is x plus s. and this is 5, and then in my smaller triangle, so I'm just drawing them separately, this is 2.4, and this is S, okay? So there's two ways I could set up a proportion like this, okay? I could work with one triangle on one side, so here S over 2.4 equals, and as long as I keep the same order, the ratios are going to be the same. So in this case here, I started with this side length, which corresponds to that one there. So x plus s in the numerator. And then this length here corresponds to the one in the denominator, so over 5. Okay, so that's one way of setting up the proportion. Another way of setting up the proportion, essentially it's the same as just cross multiplying, is starting off with the corresponding sides. So I could have also written, 2.4 over 5, these corresponding sides, is equal to s over x plus s. Okay, that would have also been perfectly reasonable. And when you think about it, it's just a cross multiplication of the original one. Okay, so questions 5 and 6, a little more interesting. Again, I would strongly recommend that you give them a try first, and I strongly recommend that you do them, okay? Because you'll see some of the homework questions, some of the assignment questions, a little bit tougher. But again, you're going to see that the tools that you need to solve those two problems are to be found in the tools that we used in these questions here, okay? So I'm going to stop the recording now.